Professor will be joining us in some time.
Okay.
Good evening, ma'am.
Good evening. We will do some problems on the topics we saw on Monday, state space analysis. So we have seen what is the difference between a transfer function and a state space model and how to represent a state space model.
Not taken any class earlier.
What?
Uh, Professor Ram is joining for the first time as a live session, or earlier also he took any classes or what?
Not in this run.
This term.
This is
Okay.
the first time sir is joining me.
And earlier he was.
Am I audible?
Yes, ma'am.
Yeah. So we have seen some basics of how to represent a system from differential equation and convert it into a transfer function, and from transfer function how can we change it to state space, and if we have some state space model, how can we take it back to transfer function, and these are all the different representation of the system, and we have seen what is the advantage and disadvantages of transfer function and state space, how to represent what is a common representation of a state space model, and we have seen some basics of state transition matrix, and what are all the solution to a state transition matrix, and how can we easily solve a problem or make a solution to a problem using a Laplace and inverse Laplace instead of going through all the Taylor series and substituting, finding a power 2, a power 3 and all. And lastly, we have seen some basics of linearization, how to convert a nonlinear system to a linear system using a Jacobian matrix, and how to find a equilibrium point, and how to do local linearization, that is linearizing around its equilibrium point. So we'll solve problems based on these topics today. First one, I will consider a system. Am I sharing my screen? No?
No.
Oh, okay. Forgot. Okay, right. I have written all these things so far. So we saw all this basics, whatever I have told so far, I have written it here. Now we are going to solve some problems. So the problems start like that. Consider the system described by a state space model. Its dot is equal to 0, 1, 5, minus 1, x plus 1, 2 into u, y equal to 1, 2, and x. Now, can you identify the name of the matrices here? What is this matrix called? How do you identify this?
The state matrix.
State matrix A or state transition matrix. This is a
Input matrix.
input matrix B. This is a output matrix C. And this is your state variable. This is your input variable. And these are all state transition or state trajectories that you can see. how over a period of time or over a period of iteration, how the states changes from one point to another point. That trajectory information will be held here. Right. Now, the question is, what is the transfer function of the system? So it's straightforward question. They have given a state space model for a system and asking back the transfer function. We know this formula. You remember this? C into Si minus A, the whole inverse into B plus D. So D matrix is not given, so it is considered to be 0. Just that you have to substitute all the matrix here. We identified what is C, A, B. So C I am substituting S 0, 0, S, because this is a second order matrix, minus, or 0, 1, 5, minus 1. This is Si minus A, the whole inverse, into B matrix is 1 into 2, plus 0. D matrix is 0. So it will be 1, 2, and doing Si minus A, it will be S minus 1, minus 5, S plus 1. The whole inverse into 1, 2. If I want to take only inverse for this, first I would do a determinant. Determinant will give me 1 by S into S plus 1 minus of plus 5, right, into into S plus 1, S adjacent I want to take. So plus of 1, plus of 5. Now this will be S square plus S minus 5 into 1, 2, S plus 1, 1, 5, S into 1, 2. 1 by S square plus 5 minus S minus, sorry, plus S minus 5. This will give me 1, 2. This is 2 cross 2. This is 2 cross 1. So output will be 2 cross 1 matrix, right? So this will give me S plus 1 plus 2, 5 plus 2 S. This is 2 cross 1. This is again 1 cross 2. The output will be 1 cross 1. S square plus S minus 5 into 1 into first row. That is S plus 1 plus 2 plus 2 into second row, plus 10 plus 12, sorry, 4S plus 4S. Now this is S square plus S minus 5 into S plus 1, we can write 4S plus S 5S plus 12, 13. So the overall transfer function is 5S plus 13 divided by S square plus S minus 5. This is the transfer function from the state space. Any doubt in this problem? The method to convert the state space into a transfer function is this. Just in this formula, you will substitute all the given information and find the transfer function model out of the system. Both are representing the same system but in different kind of representation. That's it.
Ma'am, what you highlighted that was given in the question or you have taken out? This
Oh, this is what
CSI.
we saw in the this is what we saw in the Monday class, right? While content revisit, we saw how to convert a transfer state space to a transfer function. This we saw that.
Acha, okay, now I see that that you taken A. The X coefficient is A. The that U coefficient is
Yeah. In general, a state space model will be represented using this equation. x dot equal to ax plus bu, y equal to cx. This is a pair of equation. We call this is a state space model, right? This is a one of the representations of a system. We can represent even this type also for a system. So here, whatever comes before matrix comes before the state variable x, that will be called as system matrix. It has all the characteristics of the system, how the system behaves, and what are all the, if the system is actually stable or unstable, all the informations will be stored in this A matrix, which is called as system matrix or system state transition matrix. Both we will call. The matrix that is before U, that is called as input matrix. It tells all the characteristics about the input given to the system. C is the output matrix. So it tells all the characteristics about how the output comes out. What are the behaviors of the output? If the system gives out a critically damped output or over damped output or under damped output, all the information will be stored in the C matrices. There is a D matrix that tells the relationship between input and output. Mostly this will be zero because we don't need that kind of information. It's a like additional information that we can have, but it is not necessarily to be there. So we have all this information. So this is a general representation to transfer from one representation to another model representation. One is from state space to transfer function. If you want to do transfer function to state space, then again you have to use Laplace, differential equations, Laplace and inverse Laplace. So this for converting to state space to transfer function, this is a shorthand notation. It is given in the presentation. While doing content revisit, we saw this. Is it clear?
Yes, ma'am. Ma'am, like,
Yes, ma'am.
how do we kind of do some learn about the stability and all from this state space matrices?
That's what we saw now. We use eigenvalue of A. So if this eigenvalue of A is less than 0, then the system is stable. If the
Okay.
eigenvalue of A is greater than 0, then the system is unstable. Why do we use eigenvalue here is because our state space model representation is like that. This is similar to what we use in eigenvalue representation, right? AV equal to lambda into x, where this is a eigenvalue, this is the eigenvector. Right. So a system that has been represented using this, so this holds the information about its system characteristics, right? So if you find the eigenvalue of this A matrix, system matrix, then you will know how the system behaves, whether the system is stable or unstable. So based on this eigenvalue of A, you will get to know whether it know its stability basically. Just finding the eigenvalue will be suffice.
Okay.
Right. We will solve few other problems. Okay. This is one typical problem where we can say x dot x1 dot x2 dot is equal to minus 4 1 minus 2 minus 1 x1 x2 plus 0 1 into u. If this system has input. So for u of t will be a step input. If I give u of t as step input, what is the steady state value of SS value means steady state value of x1 rounded to two decimal places that we don't need right now, but I just for the answer sake they have given in the question. Right. First we need to find the steady state value. So do you remember what is steady state value we have seen in terms of state space in the bowl problem? What do we call it steady state here?
The equilibrium.
Equilibrium. So equilibrium is the steady state value of that. So for the equilibrium, we have seen the intuitive reason behind it, why we are equating to zero, right? So when x1 dot holds all the trajectory information of x1 of t over the period of time or over the interval. So when there is, we are checking if there is any change in x1 of t2, x1 of t2, t1 to x1 of t2. If there isn't any change, then the x1 dot will be equal to zero. That's why we are equating x dot equal to zero to find the equilibrium points. Here also, steady state is also equal to equilibrium. So what we have to do? What we have to do now? We have to equate this state's trace trajectory x dot equal to 0. So it will be x1 dot equal to 0 and x2 dot equal to 0. So equating this will give me minus 4x1 plus x2 equal to 0 as first equation, minus 2x1 minus x2 equal to 0 as the second equation, right? Can you solve this? You're doing problems on it. You can take controllability observe.
So,
Is it?
and use your lab.
Yeah, I can.
You got it there.
Yeah. I will just finish this problem. So we'll solve this equation to find the x1 and x2, right? So this will be plus, okay. I'm considering plus. So this will be minus 2x1 or wait, minus 4x1 plus x2 equal to 0. Minus 4x1 plus x2 equal to 0. This is first equation. Second equation into minus 2. That will be 4x1 plus 2x2 equal to 0. So 3x2 equal to 0. Again, x2 will give me 0. Will be 0, right? So substituting this again will give you 0. So as u of t, here we are considering as step input, we can substitute u of t is equal to 0 and solve this equation again. That's what we are doing here. We are not considering u because we have considered step input. Here u is supposed to come, but we are considering u as 0. Okay. So the solution would be 0.17 and x2 equal to 0.6. Okay, let the professor join the meeting. 1 minute. Mic is almost.
Thanks. Okay. Hello. This is Manoj Pratham. And this T is you, no, right? Hmm? Student. Okay. Yep, yep, yeah, okay. Um,
Good evening, sir.
Good evening,
Hi.
sir.
Hey.
Good evening.
Okay. So I've been thinking of joining a call from long time, but today I could. I thought I still got late, so I also thought I can just take a little feedback from the course or a little, general things of what you people do, why you are into this course, and all that. So maybe we can have a just maybe some 5 minute conversation on that before I start talking about subjects. So Manoj, can you tell where you are from and what do you do and all that?
Hello, sir. Good evening, sir.
Yeah.
Sir, I'm from Madurai, and I'm actually working right now, and
Hmm.
I'm interested in nanoelectronics. So I wanted to take this course and do masters in nanoelectronics. That was my goal.
Okay. Okay. Good. So where do you work currently?
So in Madurai, sir.
No, what company, what industry you work?
Right now I'm working in a startup in Madurai.
Sort of. Oh, okay. Okay. Pratham.
Good evening, sir. How are you?
Yes, sir. Yeah. Good. Good. Thanks. How are you?
Yeah, yes, sir. I'm doing this degree standalone, and this is the last
Standalone.
term of my. Yeah, this is the last term of my diploma. From the
Diploma.
next
Okay.
term, I would be in. From the next term, I would be in BS degree level.
And where do you come from?
I'm from Sambalpur, Odisha.
Oh, Sambalpur. Nice. Okay. Okay. Good. And who is T? That's all I can see.
No, my name is
TR guy.
Gayatri.
Your name
TR
is
Gayatri. TR Gayatri.
TR Gayatri. Okay. I can only see the T here on the screen. Yeah. So Gayatri, where are you from?
I'm from Chennai only.
Okay.
Uh, so I'm a homemaker.
Hmm.
Uh,
Hmm. Hmm.
so I've been out of job for a long time, almost 2 decades.
Oh,
Uh,
okay. Okay. Interesting. Okay. Okay. So how are you liking the program and the course in particular?
it's fantastic. It's a kind of I would have never dreamt of such a course.
Okay.
From the,
So the lectures plus the live sessions are going okay. Because I don't know. I taught a course earlier for NPTEL. Now I'm doing this for here. So how is the transition happening? Is it too high content in math, or is it bearable? And how do you or any suggestions for us to make it better or more accessible?
Yes, sir. I do have one suggestion.
Yeah, please. Yeah.
So the nature of our degree is based on like term to term. So like
Hmm.
in this term, we should also practice the previous term questions.
Hmm.
So
Hmm.
that is lacking in our actual degree. So
Can
like
you
in
give a little? Can you give a little small example of that? What do you mean by term to term and previous degree practice is missing?
like in 1 year we have three terms. First term is
Hmm.
from January to May. The second
Yeah.
term
Yeah.
from April to August, and the last term is from September to December.
Hmm.
So this degree launched in the January term, this
Hmm.
2025.
Hmm.
So it's also like questions are okay, like moderate, not like too difficult or not like too
Hmm.
easy.
Too
So
easy.
you have to
Hmm.
work it out. So I just thought that I could score more little bit
Hmm.
just by
Hmm.
practicing, because sometimes we ask for the mock question. Generally, like signal systems and digital signal
Ah.
processing is also we are doing.
Uh-huh.
So they just do give at least one paper and instructors solve it throughout
Hmm.
total paper.
Hmm.
Either it could be the paper made by the professor or the last term paper. Like it
Hmm.
quiz one. So
Hmm.
we will take the quiz one of the last term
Hmm.
for practice.
Hmm.
So that we can do. So from the last term we are asking of that of this, because the last term I won't able to make
any good marks in control. So therefore, I'm repeating this course actually. Yeah, this September term.
Okay, so what, I didn't understand. What is your question? You want to do more practice problems, or you want to do a mock quiz, or you
Huh.
want so that I give you question paper and then you. So I didn't
No,
understand what your concern is.
practice on the previous questions
No, because see,
uh,
there is a lot
that
of
came in our
assignments.
quiz one.
There are assignment questions. There are textbook
Yes,
questions. So largely, it's like you want to be spoon fed of this kind of question will come in the exam, and if a little number change will come, then you will able to solve the problem.
no, sir. It's not actually happening. If you ask me, like, if you know the Tony sir is our instructor in DSP.
Uh,
So he does all the things like what I just suggested. Then also the student also not able to cope up with the. I still able
exactly.
to
Yeah. Yeah.
470.
Okay. So
Only
I
for the
think.
practice, I want to do the previous year and the mock questions
Okay. So for
just
practice.
to increase some what should say
Okay, so
confidence before
no,
exam.
so your confidence you increase by yourself. I mean, there are so many textbooks and all. We give assignment problems. You can practice from anywhere, and if you have doubts, you can ask us, right? If I look at a general IIT system, we don't do mock tests and all, right? We do our lecturing, we do tutorial classes, and yeah, that's all. And then the exams come, right? So, anyways, I think you want mock questions to be solved. We are doing, right. We are doing questions in the live sessions. So I don't really know
Yes,
what you really want to
we
do.
are doing. Yeah,
So
we are doing.
anything more than that is largely looking at spoon
At least
feeding
one
that.
paper.
No, no, you
No
should
spoon feeding. At least one paper.
no. What one? So is there any doubt that you had that we were unable to resolve? Where you tried to solve questions on your own from either your other assignments or textbook or any other online resource. So today having resources and source of problems is not an issue, right? Because there are so many free resources that you could find. I think even most PDFs of textbooks are also online.
Mm,
So
so if I
any.
say, so
Hmm,
if I say what variation comes in, like I tried some Routh-Hurwitz questions and
hmm,
Nyquist criteria questions.
hmm,
So that was very much good. What Chakravarti sir has done in our life class this term.
hmm,
But in our like our number of questions are less. There are only 11 to 12 questions. So just round it off to 10. So if I
hmm.
able to not solve to 1, so it will decrease to 90%. So what it's like that we haven't discussed about the body plots and some of the kinds, and after the quiz 2 we are coming into it. So before seeing your lectures, we
Hmm.
have the good amount of questions like the transfer function are also we have done, but that level is not means a little much different because the paper is also our what
There
should
has
I
to be
say
some surprise element in the paper, no?
CBT mode. It was not surprise. How can I say means it's not surprise. It was doable paper,
Hmm.
but the questions the quiz requires means after the practice sometimes it's not able to go with the total paper. So that was the thing.
Okay. Anyways, the onus is not on me to really give you all kind of questions that will come. Then
Okay.
it's you have to practice yourself and say, look. So my delivery would be related to if I am covering the syllabus enough, if I am doing enough problems, both from concept versus practice point of view. But if you really want that, I give you question number 1, 2, 3, 4, 5, and very similar questions will come in exam with two, three
No,
values
not
changed.
very
I
similar.
think
Means
uh, I think
in
that
signal
is
system is every time happens that mock paper is totally different from the quiz one
yeah,
what it comes.
so there is nothing. It's just psychological that you think there is no mock exam, therefore I am not doing well. Even I do a mock exam, things will change. But is there anything that we lack in terms of in the live sessions? We do 5 hours of sessions. We do
So
problems. We do concepts.
sometimes it
Uh,
happens that how you should solve the questions
so
means the quiz
sometimes, sir,
question.
therefore you have to take a problem by yourself. How many problems you have taken by yourself and solved it completely without solution? Can you have taken the problem from a textbook, say problem number 1 to 5, no solution is there. Have you started from just a problem statement till the solution? How many have you practiced by yourself like that for problems which do not have solutions, or which is not done in the class or in the mock exam for any course? So tomorrow life will not offer you only solved problems, no.
Okay, sir.
So just think of that. I think no, I kind of don't really agree to that mock exam that I do a mock and then very
Okay.
similar things will come to the class. But if there is anything that you had a doubt in, some say you took up a problem from Ogata or Nagarath Gopal or whatever the questions you are not able to solve, you come to us, we helped you or not. If that loop is closed, then I think we are kind of doing okay in that. You understood? Okay. Anyways,
Yeah.
so we'll talk through a little bit of concepts also, right? So,
Yeah.
um,
Yes, sir. We can go further.
yeah. So largely, I'll just do of what it's meant by controllability, right? So I think we would have done in the how many of you actually watched the lectures fully?
Yeah. Yes, sir. I do.
Yeah. Okay. Good. So what does it mean by controllability, and why do you even look at things, right? So suppose now I have a small, say there's a two-wheel system, okay, and if I say like this is a car, right? I just take maybe the rear or the front wheel. So a control would mean the following, that I should be able to take my car from any point A to any point B here. Right? So I start from here, I should be able to go here. I should be able to maybe go even here. Okay, like this, and maybe park it this way, or even park it say at a 135-degree angle and so on. Okay. Now, what are the controls that are required for this? So, say assume one control is I can go forwards, and when I say go forward, I can also say I can go backwards. Now, can I call this system as controllable? Right. So again, what is the thing that I should be able to go from any point to any other point, and maybe even at any other configuration, right? So if I can just go forward or back, it will just mean that I am maybe I can just go here, or I can come back here. But to go to here, what do I need? So to go here, I also need a steering angle, right? So I'll steer the car. I'll go. um I'll go forward. Then I'll do a steering and then come back here, right? So when I say a system is completely controllable, means I should be able to go from any point. Like my car should be able to not just go from Sambalpur to Raipur, but it also should be able to go from Sambalpur to Madurai, or even Chennai. So these are the systems which are completely controllable. If I do not have a steering control, I can still do something with the system, but this will not be completely controllable. Okay, so in my setting, what am I looking for, right? So now I have things which are, well, I can now write down systems in the state space formulation, and I'm assuming remember this properly. So I have x dot is ax plus bu. The state transition matrix you have done, or in the class, or not yet?
Yes,
Yes,
sir.
no,
We
yes. Ah.
last class, I guess we have.
Last task we have done. Okay. So I have the state transition matrix. So with the state transition matrix, I'm able to find the solution to the unforced system. Unforced system is largely that x dot equal to ax, and which has a certain solution. In the linear LTI case, it turns out that x of t is e power at times x naught. Okay. So that is with the state transition matrix. Now, what happens when I have so with the unforced system? Unforced system could also mean, say you have a fan, and I just switch it off, the control goes away, it just comes back to rest, and that's how also we define the stability of a system, that the impulse response should go to zero. Or if a fan is rotating, I just push it a little bit, it'll again come back to rest. So there is no forced response, it's just the unforced response. Okay, now what happens when I have a non-zero control input, that I switch on a fan, and I consistently give it a voltage of 230 volts. And it is it could be a constant signal, it could be time varying, it could be just a constant of u equal to 0, or it could be a signal which is sinusoidal, and so on. Okay, now what do I mean? So when I say I'm looking at x dot equal to at, sorry, x dot equal to a xt, I just integrate both sides, and get a solution that x of t is e power at with x naught. Okay. Now, same thing is here. We do is we look at finding solution. Uh, uh, is again equivalent to integrating the system. In integration, of course, I'll just skip the steps of integration. But what we will see here is that, well, I have, of course, my the response. So this is my natural response, and this becomes my force response. Okay, force response is the response which comes after the input. So now I just look at the system. So what I claim here is that x of t is e power at x naught, and then you do this little integral which also includes the input matrix, or the input term b, and the input signal. Okay, so I have a scalar system again of the form. So x dot is di by dt is minus r over li plus Vs by L. So I just have things of this form, right? So I have I of t will have the response. This is my natural response, and this is my force response. Okay, now let us say a situation where, say, Vs equal to 0 and I naught equal to, say, some value 1. So what will be I of t? I of t will now be e power minus r over L times t times 1. So if I look at what is the steady state of this, steady state in the sense, what is limit t going to infinity e power minus r over Lt? What would this be? It will simply be 0 because the system is stable. Okay. Now assume another situation where now let's say the initial current is 0. Okay. Then, and this is some Vs equal to, say, some say 1 volt. Okay. Now I'm looking at my solution. I of t is 1 minus e power minus r over L t times 1 over r. Okay. Now first is what happens at t equal to 0. What is I as 0? I as 0 is 1 minus e power 0 will be 1. So I of 0 will be 0. So if I were to plot a graph, I of 0 versus time, so it starts at 0 at t equal to 0. Okay, and then what happens at t equal to infinity? So I of t with the limit t going to infinity becomes 1 over r. So I start from here, and slowly I reach this line, which is 1 over r. Okay, that is the how you look at the standard response of a first order system. Okay, and therefore now equivalently it's a little laborious process. Now I can show what happens when you have, instead of a scalar, you have a matrix. You have terms involving your state transition matrix. So e power at will now be a matrix. Okay. Similarly, now I can write once I know what is x, I can find out what is the y. Okay. So again, some quick examples here of uh, how to determine the state transition matrix for certain sys input. So I'll skip this. We will. This should be, I think, straightforward. In all the steps are written down. Okay, so I'll just do the concept. I think we have about 15 minutes Still to go? Yeah. Okay. We have a little more than 15 minutes. Okay. So what is now the system? What is now the concept of controllability? Right. So I start with the system of this form. Okay. And then now I arrive at a solution which is largely like this. Right. So again, this is the state transition matrix. Here are the input matrix, the input signal, and so on. Okay, so we will not really at all times try to integrate systems, but we will try to do it a little more subtly. Okay, so a system is controllable if there exists an unconstrained control signal, right? So I don't really, or if I ask a question, can I design a car which will go from Chennai to Sambalpur in 1 hour? Okay, the answer would be yes. I may really need a very powerful engine, more powerful than sorry, an aircraft engine, so that I can just go from Chennai to Sambalpur in say 1 hour. So I don't really look at the constraint on the signal. It can be however large it is. Can I go and buy it off the shelf, or can I buy that big motor, or which can generate certain torque, or that much engine which will give so much energy? That is not the point, right? It can just be unconstrained. Okay, that will take the system from any initial state x naught to any desired final state. And if I look at that, if I were to just go around a car, I should be able to start from here and go at any other point in the state space. Okay, so if an input to the system can be found that takes every state variable from a desired initial state to a desired final state, then the system is said to be controllable. Okay, now of course we will look at when I can control the system, then I can control its transient response. I can design it for a certain overshoot, I can design it for a certain steady state error, and so on, right? So the definition requires only that the input be capable of driving the system anywhere in the state space. In of course, this should happen in finite time. I should not reach Chennai to Sambalpur, say asymptotically at t equal to infinity. So all this must happen at finite time. And of course, what trajectory it takes is also not useful. Maybe I can go via Nagpur, or I can go via I don't know, Bhopal or something like that. That trajectory is not very useful. Okay. So okay, we will look at how to first get this derivation of okay. Okay, so what is happening here is, just get this. Okay, so we start with the system of the form, again x dot equal to ax plus bu, or without loss of generality, again we can assume that I started time t equal to 0. Again, it will just be easy for my computation that the initial time I talk of t equal to 0, the t naught equal to 0, and assume that the final state is the origin, which means if I start here, say this is my entire state space in which I want to control, I will just, for ease of computation, say that I'm starting from this point and going in whatever ways and at this point. So at t equal to 0, I am some initial condition x naught, and at x equal to t1, again this is finite time. I am assuming that I'll come to the origin. Okay, now my equation becomes simple. So again, what is the control problem? Starting from x at 0, could be whatever x naught, I should be able to reach any x of t. Okay, so the state controllability definition requires that given any initial state x0 at time t equal to 0, we should reach the origin in finite time. I'll call that x at t1. So x at t1 becomes 0, and now I have something like this. Okay, this is an equation now where of course a is unknown, therefore e power at1 is unknown. I know the initial state, I know the input matrix. It's just that this is an equation to solve with an unknown u of t. So before solving this equation, I should be I should determine whether or not the equation is solvable. So can someone give me an equation which is not solvable? System of equations which is not solvable.
A system of equation which is not solvable.
So if I say x1, we all know simultaneous equations, right?
Yes, sir. Oh, like that.
Okay. It has a solution
So they
exists to
both are,
this.
they both
So lines are
are not,
parallel, they will not intersect and so on. So
they
before
will
I
not
even,
intersect.
yeah, the lines are parallel to each other, so there is no solution, right? So therefore,
Yes.
in the same way, here I have an equation, and I am even before I control a system and I go on to buy a controller, I should first ask. The first is not to find u of t. First is, can I control the system, right? So can I control the system? That is a question which we will ask. Now, what is the system? System largely is A, B, C, and D. Similarly, yeah, what do you do? So, if I say stability of the system, most people would say bounded input should result in bounded output. I don't really give input to the system, right? What I do, I just look at poles of the system. And poles of the system are largely again related to the system properties A, B, C, and D. Okay, so similarly now I do something like this. So now my this is 0. I have the unknown as u tau, and I say under what conditions the solution will exist. I can rearrange terms, and I get something like this now. Okay, and then a simple expansion of e power a tau will look like this. Like in this details we will skip. So what happens now is that I now have an equation which has the initial state here, a matrix here, and this beta. This beta is computed as a function of u tau. Right? So this is, if I look at the left hand side, right, x naught is known. Okay, this is also known. It's a matrix, and somewhere here is the unknown. Okay, it's largely saying that I have an equation, say ax equal to b. Okay, I can say, when is the equation solvable? The equation is solvable if I just take that, A is a square matrix, and if I'm looking at a unique solution, x must be equal to A inverse b. Similarly, here I have something like that. Right? So here this is my unknown. I can call this as a system matrix A. Here it is a C matrix. Say similarly, right? I have C times beta equal to x naught. As simple as ax equal to b here. Okay. Now, where is the beta? Beta comes from, which has the unknown control term, so this will simply be C inverse times x naught. This also means that the condition for complete state controllability, again, this is a single input, single output case, requires that A is invertible, or a matrix. When is a matrix invertible? When it is of full rank. Or the condition that I am looking at checking is that the rank of C is equal to n. That is the condition how I check for controllability. Whether a system is controllable or not is largely done by checking. Again, look at this. These are just system properties, right? There's nothing to do with the input. It's system being controllable or not doesn't depend on, of course, the dimension of the state space or even the nature of inputs. If it is controllable for one input, it should be controllable for all inputs. So controllability is also therefore a system property. Okay. Now, of course, what happens when there are more systems? So when there are more inputs, it's the same thing, right? The results can be extended easily to system with m inputs. Just that the rank condition still remains the same. That the rank of C, this must be equal to n. Okay. Now, the following statements therefore are equivalent, that a pair AB is controllable is equal to the controllability matrix. So this matrix now I call as the controllability matrix. It says that the AB is controllable if and only if C, this matrix C has full rank. Okay. So first is, what have we done now? First is we define controllability. And second, I check before I apply any control law. Is how to check for controllability. Okay, these are two things that we did before we actually try and control the system. So this is a simple example. I have x dot equal to ax plus bu, and then I can just look at the rank of the matrix b times b. This is 1001. The rank is 1, and therefore the system is not controllable. I can also see, right, why is it not controllable. If I write down the equations, I will have x1 dot is x1 plus x2 plus u, whereas x2 dot is equal to just 2 times x2. So there is no explicit control in x2 dot. Okay. Now similarly, if I do another example, say x dot is 0, 1, 0, 0, x plus 0, 1 times u. Okay. Now first we'll check is the system controllable. I look at the B matrix. So B is 0, 1. What is A times B for this? Is 1, 0. So the BAB matrix is 1. What is the rank of this matrix? This is a full rank matrix. Rank 2. Therefore, this system is controllable. Again,
Rank
what does it mean, right? Yeah, correct. Rank 2. So if I just write down the equations by themselves, I have x1 dot is x2. x2 dot is u. This is also called as an integrator system. Okay, in the first case here, what I see is that the second state variable, I'll come back to this example again, which is printed here. X2 is to x2. The second state variable x2 is completely decoupled from the input. So whatever I choose input here, however large it is, it doesn't do anything to x2. Okay, and therefore no input u can directly affect x2 or even indirectly. Thus, we cannot control the system to any arbitrary state. Whereas in the second example, I have x1 dot is x2, x2 dot is u. Of course, x2 directly affects u, but after through x2 I can influence x1. So first is I start with u, which influences x2, and indirectly I can influence x1 now, right? So here you see, right? x1 dot is x2, but x2 can be controlled by u. Whereas here x2 dot is just to x2. Just by controlling x1, I am unable to control x2, right? So that is a little distinction here, right? So no u input u can be directly or indirectly affect x2 in the printed example. Thus, we cannot control the system to an arbitrary steady state. Okay, now what is also happening, again, we'll not do the details of the proof here, is that what happens when the system is not controllable, and because we did a lot of analysis on transfer functions, and okay, I'll just stick to this example. Okay, so do we know how this formula comes from? This particular one? Okay, so I have x dot is ax plus bu, y is cx. So I just do a Laplace transform. So I have s times xs is a xs plus bu, y of s is c x of s. So I rearrange terms. What is my Laplace transform? Is the transfer function Laplace of the output to the Laplace of input. It just turns out to be, I can just arrange these terms. I'll have c si minus a inverse b. Yeah. Okay. Somebody typed down something here. No.
No, sir. Actually, one our control engineering course joined the session.
Control engineering course. That is you. Okay. 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 So how much time we end at 3:30? Okay, so I'll just finish it. So what I do here is whenever there is now I just look at what happens to the transfer function, right? I just again use this simple technique to go from the state space to transfer function, and what I see is that okay, so I compute the transfer function. What I see is that there is this there is a pole to zero cancellation. Okay, so this indicates that the pole at s equal to 2 was cancelled by a 0 at s equal to 0, saying that the pole at s equal to 0 is uncontrollable, meaning it cannot be influenced by the input u. So what was the pole at s equal to 2? Largely sitting by this number 2 here, this guy. Okay, so whenever the system is not fully controllable, what we see is that there is a pole zero cancellation, that the control input can no longer influence the state of the system associated with that particular cancelled pole. Okay, so here I look at another system with a certain A, B, and C. I compute the rank of the controllability matrix. It's a full rank, and also you see that there is no pole zero cancellations here. Okay, so one way how does it reflect in the transfer function thing is that there will be a pole zero cancellation when you go from the state space to transfer function to you can check for whenever there is a cancellation, the system is not controllable. I think we just are out of time. I will stop here and maybe take a couple of quick questions before we end the session.
Yes, sir.
Okay, any questions? Yes.
Yeah.
Sir,
Sir.
one more suggestions.
Yes, please.
Sir, in the first few lectures, whenever you are discussing any concept, you gave some examples, and also in the end of the lectures, you posted some questions for the students to think about it, and then the next lecture you started with the same. So likewise, if you are able to do it for all the lectures, then it will be.
Yeah, I will be able to do all the lectures. Okay, I think the initial things you do because you can have to used to that kind of thinking at the systems level, right? Of how does the
Yes.
transition happen, and now I think because we speak different, you're not used to the languages when I just talk of Laplace transform or stability or state space and so on. So slowly in the transition to, when we learn languages, we learn through little songs and nursery rhymes also, right? So I'm now assuming that we can speak the same language, and that whenever I say a system, it actually means either a transfer function or x dot equal to x plus bu. But I can do that. Maybe we can kind of ask few things and put up some questions. So that those were initially to just get you a little initiated into this idea of the language of control engineering, starting from how do you use math tools to actually implement or actually design and implement controllers. And I think Pasumarthy does a lot of examples, include and Chakravarti also. So they design autonomous vehicles. They do a lot of things from all the way from sensing till actuation. Maybe I can ask her one of the days to just show you what she actually does in the lab to see where all these concepts are used. So maybe we can just have one session where we just discuss not just what is in the slides, but a little more than that, right? We can maybe do that. But okay, your suggestion is okay. I can just maybe just add some questions at the end of this.
Thank you.
Okay. Any other questions, suggestions? Yes, madam.
In week 8, the graded assignment was very tough. The design,
Good.
those
It is supposed to. Okay, so I think what I can do is, I can ask Vasumati to actually explain the solution bit by bit. Is that's possible, no? So I think because Pratham was complaining that we are not doing enough questions for the quiz, but the design you can do it. Explain the solutions part by part, and
Yes, sir.
don't
For designing also. Yes,
design
sir.
we can do again at some point of time you have to really get to the question and start solving yourself. The learning happens not by watching but by practicing, right? If I watch Virat Kohli batting 500 times, or all his 50 to hundreds, if I watch repeatedly, doesn't mean I can be a good batsman. No, I have to take a bat and do. So what I would suggest is you take some problems if you are and you learn by mistakes, right? Not that, oh, this all, I take a problem, I solve it, I take a problem, I solve it, and it's so also do that. So design, I will ask or maybe I can do one session on just how to think about do the thinking before the we just apply it after the once you know the concept, then it's formula based, right? That, do this, find the pole, find the zero, then design the k and all that. That is just the process. But the pre-processing also we will try to learn. I just ask ourselves questions of why we are doing it that way, why not some other way. Don't learn it as a sequence of formulas, right? Then it may go wrong, because my questions usually will be a little twisted, where it will need a little thing, a little thinking beyond one or two problems that we do in the class. So the design we'll do a little more extensively. Yeah.
Thank
Or
you.
maybe you can record and post it if live sessions it's not possible.
Based body plot, I showed all
So
the
one of the assignments you can just solve for them.
Thank you, sir.
Yeah. Okay. Good. Thanks. Maybe I'll see you maybe one or two more times before the end sem.
Yes,
Let's
sir.
Yeah.
Yes, sir. Thank you, sir.
Okay. Good. Thanks.
Thank you, sir.